Good day. So today we are to proceed to our next topic, the design of column base plates. So column base plates are used as a steel concrete interface between the steel columns and their foundations. So their main function is to transmit the structure stresses to the concrete footing surface and to link the column bottom end to the footing. So column bases include base plates, anchor rods, then we have shear resistant elements. Example is we have the shear lugs. So steel connections are the ones who are ensuring the structure stability and must realize the best possible way the type of internal link considered in the design. So this is one example of the link between a steel column and its concrete foundation. So basically for a steel column, so it is, for example, subjected to a compression load. So let's say PU or the PA. So we have here our base plate. So other than the base plates, we have the inclusions. So we have the anchor rod, the grout. So the purpose of the grout is basically to make sure that the stress coming from our steel column, which is a compression member, will be uniformly distributed from the steel column to the concrete pedestal. And this is our concrete footing or the concrete pedestal. So a while ago we have this shear lug, so steel embedment. The purpose of steel embedment is to transfer the shear load from the column to the footing. So let's have its top view. So for example, we are using a wide flange. So we have the width of the flange, B sub F, and its depth D. So this is basically the area of our base plate. Okay, for the base plate, so we are using A sub 1, that is basically B times the D. But in some references, the D is the same as the N, so we can have area 1 is basically B times N. So this is the area of our the base plate. So what are the computations necessary for the design of the base plate? So we have here the P sub P, that is equal to 0.85 of FC prime area 1. So that is if we have the minimum area of our base plate, that is the same as the dimension, let's say the outer dimension of our wide flange, the B sub F times the D. For the cases that the dimension of the base plate is only equal to the depth of the flange multiplied by the depth of the flange multiplied by the width of the flange, the wide flange. So basically, if our the required minimum area, or this is, let's say, the minimum area 1 is simply the B times B sub F times the D. Then we have area 2, that is the area of the supporting concrete or the area of the concrete pedestal. So we have a consideration here. So we have P sub P multiplied by P sub P, or the nominal bearing capacity of the concrete pedestal, 0.85 FC prime area 1 multiplied by the square root of area 2, the area of the concrete pedestal divided by area 1 should be less than or equal to 1.7 of FC prime area 1. So we have the limit of this factor, area 1, or the square root of area 2 over area 1 should be a maximum of 2. So for bearing stress, we have our reduction factor, 0.65 for LRFD, and ASD is 2.31. So again, the D dimension of our base plate is the same as N. That's equal to the square root of area 1, the area of the base plate, times delta. How do we compute for delta? So we have here our equation. So we have this a while ago, the area of the base plate. Then for the required thickness of the base plate. So obviously, if we can compute its dimension or its area, so also we need to decide, or we need to design its thickness. So we have two equation here. So based on LRFD and ASD. So we have this L. So again, area 1 is the area of the base plate. So L is the largest of M, N, and lambda sub N. So what is M? So can be computed based on the dimension of the base plate. So this is our M, N. So we can compute them if we have the value of the N and the value of the B. Well, for the lambda sub N is equal to the square root of the depth of the wide flange, then B sub F divided by 4. So all we have to do is follow these steps. So computation of area 1, area 2, the thickness, and so on. So this is just our basis for the plate area. So let's have an example how to design a base plate. So let's have this example. A W section is used as a column and is supported by a concrete pedestal as shown. The column will support a service dead load of 450 kilonewtons and a service live load of 650 kilonewtons. So determine the dimension of the base plate using LRFD method and NSCP IASC specifications. So we have our loadings. We have for the dead load, P sub D is equal to 450 kilonewtons. Then for the live loads, we have 650 kilonewtons. So we are to use a wide flange or a W section, W10 by 49. The base plate will be A36 steel. Fy is equal to 248 megapascals. So concrete pedestal, we have now its dimension, 450 mm by 450 mm, and its Fc prime is equal to 21 megapascals. So let's have the properties of the W10 by 49. So from our database, so let's have Control F, the W10 by 49. So I think I'm on the metric system, measurements, so millimeters. So the area is equal to 9,290 millimeters. The depth is 254, and the width of the flange is the same, 254 mm. So for the properties, we have its area is equal to 9,290 square mm. The B sub F is equal to 254 millimeters, and the depth is also equal to 254 millimeters. So why do we need this dimensions? So basically to compute for the minimum area 1 or the area of the base plate. So for area 1, again, this is the area of the base plate. So again, the use of the B sub F and the D is for the minimum area. So we have the minimum area 1 is basically equal to B sub F multiplied by D. So let's have this values as our reference value. So minimum area 1 is equal to 254, that is to be squared, equal to 64,516. 64,516 square millimeters. So the minimum required area for the base plate. Then for our load combination, or the factored loads, we have P sub U is equal to 1.2 of the dead load plus 1.6 of the live load. So this is 1.2 of 450 kilonewtons plus 1.6 of 650 kilonewtons. So this is the first load combination. We have P sub U is equal to 1.2 of 450 and then plus the 1.6 of 650. So we have that as 1,000 ay 1,580 kilo newtons. So the other load combination or factor load is equal to 1.4 of the dead load. So let us just check. Ay 1.4 of 450. So this ay 1.4 of 450 kilonewtons is equal to 630 kilo newtons. So when it comes to load combination, the higher value will govern. So we are using our ultimate load ay 1,580 kilo newtons. So let us now compute for the required area 1. So from our introduction, so we have the nominal capacity P sub P is equal to 0.85 of Fc prime area 1, then to be multiplied by the square root of area 2 divided by area 1. But should be less than or equal to the 1.7 of the Fc prime multiplied by area 1. So what will be the equivalent of our ultimate load? That is, if we are to apply a reduction factor to our nominal capacity, the P sub P. So we'll be having the P sub U is equal to P, then multiplied by 0.85 of Fc prime area 1, the square root of area 2, then divided by area 1. So by the way, what is our area 2? That is the area of our concrete pedestal. So this is our area 2. That is a square. We have 450 squared is equal to that is equal to 202,500 square millimeters. So let us compute the required area 1 based on our ultimate load, the 1,580 kilonewtons. This is 1,580 kilonewtons, then multiplied by 1,000 to be in newtons. So again, what is our reduction factor for this bearing stress? If you are to recall from the intro, that is equal to 0.65 for LRFD. Okay, so this is 0.65, then multiplied by 0.85 of Fc prime for the concrete is 21, area 1, the square root of 202,500, then divided by area 1. Okay, so let us compute for the value of area 1. Okay, we have that as 1,580, then multiplied by 1,000 to be in newtons is equal to 0.65, then multiplied by 0.85, then 21 megapascals, area 1, alpha x, then multiplied by the square root of 202,500 divided by area 1. So that's 91,576.91. So let's say we are just to use whole numbers, 91,577 square millimeters. And basically, what is our reference value for area 1? What is the minimum area 1 a while ago? So this is our minimum area 1. So the minimum area 1 is 64,516. So this is basically greater than the minimum area 1, which is equal to 64,000, again, 516 square millimeters. So this is, okay, so this is adequate when it comes to, just to satisfy this condition, for the area 1. So what's next is that we are now to compute for the value of D. The value of D, or that is basically the value of N. So how do we compute for the value of N? Again, so from our reference, the value of N is area 1 plus delta. Or that is equal to the square root of area 1 plus delta. How do we compute for the value of delta? So delta is equal to, okay, to this equation, so 0.5 of 0.95 of D, then 0.8 of B sub F. So we have that as 0.5 of 0.95 of the D minus 0.8 of the B sub F. So if you are to double check, okay, this 0.5 of 0.95 of D minus 0.8 of the B sub F. So computing for the value of this delta is equal to 0.5 of 0.95. Again, what is the depth of our wide flange? So we have the same with the width of the wide flange. So 0.95 of 254 minus 0.8 of 254. So we have now the value of this delta is equal to 0.95 minus 0.8, and then multiplied by 254, and then divided by 2. Okay, that is equal to 19. So we have 19.05 millimeters. Okay, let us double check. That is 0.5 of 0.95 of 254 minus the 0.8 of 254. Alright, that is okay. We have 19.05. So again, so we can now compute for the dimension n of the base plate. So we have n is equal to the square root of, what is our area 1? This 91,577 plus the delta 19.05. So we have now the value of n is equal to, we have the square root of 91,577 square millimeters plus the 19.05. So 321.667. So 321.667 millimeters. So it's better if we are to round this up to let's say every 5 mm. So let's say 325 millimeters. Divisible by 5. Okay, so we can now use the value of n is equal to 325 millimeters. So we can now compute for the value of B. Okay, so anyway, so we have now the value of the D, 325 mm. So we are now computing for the value of this B. So again, what is the, how do we compute area 1? Area 1 is basically equal to B times N. So area 1 is our area 1. 91,577 is equal to the value of B, then 325 millimeters. So this will be the value of B. $91,577 divided by 325. 281.775. 281.775. If we are to round this up to a value divisible by 5, let's say 285 millimeters. Then this will give us our actual area 1. So our actual area 1, we have B is equal to 285 millimeters. And the value of our N is 325 mm. So we have that as 200. That is equal to 285 millimeters multiplied by 325 mm. So that is equal to, we have 285 multiplied by 325. So our actual area, the area 1 is equal to 92,625. Area 1 is equal to 92,625 square millimeters. So we need to check its adequacy, if it is adequate to carry our piece of view. By the way, we need to check if it is also less than or equal to the 1.7 of FC prime area 1. Okay, so let us do our checking based on its area. Okay, so again, our area 1 is now equal to 92,625 square millimeters. Okay, so computing for its capacity, piece of view is P multiplied by 0.85 of FC prime area 1, then the square root of area 2 divided by area 1, and so let's have it should be less than or equal to 1,580 kilo newtons. Okay, so let us do our checking. Okay, so we have now the piece of view is equal to 0.65 of 0.85. FC prime is 21 megapascals. Our area 1 now is 92,625. Then to be multiplied by the square root of 202,500. If you are to recall our area 2, the area of the concrete pedestal, 202,500 square millimeters divided by 92,625 square mm. So this will be the piece of view is now equal to 0.65 multiplied by 0.85, then 21 megapascals. Area 1 is 92,625. Then multiplied by the square root of 202,500, then divided by 92,625. Then to be divided by 1,000 to be in kilonewtons. That is 1,589.016. So 1,589.016 016 kilonewtons. So this is greater than the actual ultimate load, or the 1,580 kilonewtons. So we can conclude that it is adequate. So we just need to check some conditions. Let's say, what is the square root? Okay, the first one, so what is the square root of area 2 over area 1? It's so a maximum of 2 according to our reference. So area 2 is 202,500 divided by 92,625, and this is equal to it's 1.478. So this is 1.479. Yes, and it is less than 2. Then the other one, when it comes to the other condition, is that we have the 0.85 of FC prime, area 1, then the square root of 200, or the square root of area 2 divided by area 1 should be less than or equal to the 1.7 of FC prime of area 1. So let us just satisfy or check if this condition is satisfied. We have 0.85 of FC prime, 21 megapascals, and area 1 is 92,625, then multiplied by the square root of 202,500 divided by the 92,625. Is it less than or equal to 1.7 of FC prime, which is 21 megapascals, and area 1 is 92,625. Okay, for the value on the left, we have 0.85 of 21 megapascals, 92,625, then multiplied by the square root of 202,500, then divided by 92,625. And divided by 1,000, 2,444.64. So 2,444.64, is it less than or equal to Okay, the 1.7 of 21 megapascals, then 92,625. Then divided by 1,000. Yes, I think so. The condition is satisfied. So 3,306.71. So 3,306.71. So this condition is satisfied. The same with this condition. So we are good when it comes to our area 1. The 92,625 square millimeters. So with our B is equal to 285 mm and N, the dimension 325 millimeters. So for our next step is we are now to design its thickness. Okay, so let us design the required thickness of our base plate. Okay, so again, how do we compute for the thickness based on our equation from our reference? So the thickness, so we are using LRFD. So this, the thickness equal to the L, the square root of 2 P sub U, divided by 0.9 of Fy B sub N. So maybe we can just place our solution here. So we have for the required thickness. So the thickness is equal to we have L, that is the square root of 2 P sub U divided by 0.9 of F sub Y, then multiplied by B times N. Okay, so that is by LRFD. Okay, so how do we compute for the value of L? So it's either the value of M, N, or the lambda sub N. So whichever is the largest. So the largest of M, N, and the lambda of N. So based on our figure, how do we compute for the value of M? Okay, so the value of M, that is twice of M plus 0.95 of the D is equal to the capital D, or basically that is our N last a while ago. So if we are computing for the value of M, that is equal to N minus 0.95. Okay, then to be divided by 2. So this is how we compute for the value of M. So I think we do have that equation. We don't have that equation here. So M is equal to N minus, we have that as 0.95 of the D of the wide flange. Okay, so N minus 0.95 of D divided by 2. Okay, what about the value of M or N? Okay, the value of N, so this twice of N is equal to twice of N plus 0.80. 0.80 of the B sub F is equal to the value of B. So therefore, the value of N is equal to B minus 0.80 of the B sub F, then also to be divided by 2. So that's how we compute for the value of M and the value of N. So let's have their values. So a while ago we have the value of the B is equal to 285 millimeters, and the value of the N is equal to 325 millimeters. And for our wide flange, the value of B sub F is 254 mm. The same with the value of the depth of the wide flange, 254 millimeters. Okay, so we are now ready to compute for the value of M and the value of N. So for the value of M, that is equal to N, 325 minus 0.95 of 254. Then all over 2. We have the value of M is equal to Okay, 325 minus 0.95 of the depth of the wide flange, 0.95 of 254. Okay, then divided by 2, that is 41.85 millimeters. Okay, the value of M. Then the value of N, okay, the value of N is equal to B, that is equal to 285 minus 0.80 of B sub F, the same as 254, then to be divided by 2. So we have the value of N is now equal to, okay, 285 minus 0.8 of 254, then okay, to be divided by 2. That is 40.9 millimeters. We have 40.9 millimeters. So these are the value of M and N, okay, from our figure. Then the value of the lambda sub N. So we have a given formula. Okay, the value of, okay, this is the lambda sub N is equal to the square root of D times B sub F divided by 4 all over. Supposedly, it is the square root of D times the B sub F divided by 4. Okay, so it is given from our reference. So computing for the value of the lambda sub N is equal to the square root of 254. Okay, the base width of the flange is also 254. Okay, then all over 4. Right, so we have the lambda sub N is now equal to, okay, we have 254 squared. Then again, you are to take its square root, then divided by 4. So that is equal to, we have 63.5 millimeters. So this is the value of the lambda sub N. So according to our reference, so the value of the L should be the largest of M, N, and the lambda sub N. So if you are to check, the M is 41.85, N is 40.9, and the lambda sub N is 63.5 millimeters. So therefore, we are to use this value as the equivalent of our L. Okay, so we are now ready for the computation of the thickness. So the thickness is equal to, but first let us recall the given. So we have the value of P sub U is equal to 1,580 kilonewtons. We have Fy, this is A36, and it is also given Fy is equal to 248 megapascals. So this is 248 MPa. Then the value of our B is equal to 285 millimeters, and the value of N is equal to 335 mm. And the largest L, or is the largest of M, N, and the lambda sub N is equal to 63.5 mm. So if you are to recall the given, necessary for our computation of the thickness. So 63.5, 325, 285. Okay, so all we have to do is now substitute to this equation for us to compute for the required thickness. So we have that as 63.5 millimeters, the square root of 2 times 1,580. So we convert this one to newtons. So multiplied by 1,000 newtons. Then divided by 0.9. The given type of steel is A36 with Fy equal to 248. So this is to be multiplied by 248 megapascals. The value of B is 285. And the value of for a while. The value of N is 300. This is 325. Okay, so we are now ready to compute for the required thickness. So we have that as 63.5, then multiplied by the square root of 2 times 1,580 kilonewtons. We are multiplying 1,000 to be in newtons. Divided by 0.9, the given Fy is 248. The computed base is 285, or the value of B, and the value of N is 325. Okay, it's 24.826. Okay, 24.826 millimeters. If we are to round this up to the nearest value divisible by 5, obviously we can have it as 25 millimeters. Okay, so this will be the required thickness. Then for our conclusion, so we are now to use. So these are the area, and the dimension. So for our conclusion, we are to use a base plate. That is, let's say the B times. We are to use B by N by the thickness. The value of B is equal to 285 millimeters by 325 millimeters for the value of N, then by its thickness, 25 mm. So this is our conclusion for the required base plate. And this is our solution for this example.